Okay, section 8.4, electronegativity and polarity, part 2. So sometimes we want to be a little bit more sophisticated in terms of classifying our bonds as polar, or polar covalent, I should say, versus ionic. So first, let's begin with a little bit of more of the notation here. Let's say that we have a polar covalent bond for the moment. A good example of a polar covalent bond is the one that forms between hydrogen and fluorine. There is a very large difference in electronegativity values between these two elements. Remember, you can look those values up from the chart. Big difference. So it's definitely polar covalent. So one way to represent that is to put a delta plus on the element that's less electronegative, which in this case would be the hydrogen, and to put a small negative charge on the atom that is more electronegative, which in this case would be the fluorine. Okay? So the one that has the higher value of electronegativity has a negative charge, and the one that has a smaller value of electronegativity is called, it has a positive charge, a small positive charge. Okay? Another way to represent this is with what's called a dipole moment. Okay? And is done using a vector. So in this case, what you do is you represent this charge separation, right? Negative on one end, positive on the other end, with an arrow, a vector. And the vector here, the head of the vector should be pointing in the direction of the element, of the atom, that's more electronegative. And the tail of the vector should be pointing in the direction of the atom that's less electronegative. If you want to help yourself to remember, you could put a little cross there to remind yourselves that the hydrogen is less electronegative, so it's positive, so the tail of the vector is in front of the positive. That is a different way than this one up here to represent this phenomenon. And we call it a dipole moment, okay? The dipole moment can be calculated. For charged particles, okay, the dipole moment mu is calculated by figuring out what the charge on the particles are, what is the charge on each particle, and multiplying that by the distance between the particles r. So Q is electrical charge or electric charge, and r is the distance between the particles. So it's based on this idea that you have something that has a positive charge and it's attached to something that has a negative charge, and there is a distance between them. Distance r, right? So the centers of those two charged particles are r units apart. The distances are. If we multiply that by the amount of charge that the particle has. Now, the assumption here is that the amount of negative charge we have over here is equal to the amount of positive charge that we have over there. They cancel each other. So the charge that we would use for Q could be either one because they're equal to each other. Okay? So the amount of electric charge times the distance. Now, pointing out, for those of you who have had physics, the dipole moment is a vector. So I'm going to draw a little arrow in front of it to indicate that there is a directionality to this dipole moment. And that directionality has all to do with the distance, the length of distance between those two charges. Okay. Now, what happens is if we start thinking about units, the SI unit for charge, Q, is the coulomb. Okay? And the abbreviation with that is a C, capital C. For length, in this particular formula, it's R, it is the meter. And so that would be meters. So if you tried to figure out what the unit of the dipole moment would be, it would be the coulomb times meters, right? Coulombs times meters. Now, the only issue with that is that what happens is, if you actually use the actual numbers that we find with charges on atoms and the distances between the atoms, between the nuclei, they're so small that our dipole moment would be somewhere in the 10 to the minus 30 to 10 to the minus 31 coulomb meters. That's not real practical. So what we do is we come up with a way of using a related unit, a derived unit. Okay? So the way we do that, just come up here, come down here. There we go. Is we define something called a Debye. And we define a Debye, the abbreviation is a D, a capital D, is that a Debye is 3.336 times 10 to the minus 30 coulomb meters. So instead of reporting the dipole moments of these bonds as 1.5 times 10 to the minus 31 coulomb meters, we convert it to Debye to give us numbers that are more reasonable. So let me do the following. I'm going to take some values that are in your textbook, and I'm going to put in here, so this is from table 8.5. Here are the bonds that we're looking at. The first one is HF, the second one is HCl, then HBr, and then HI. And then next to that, I'm going to put down the bond lengths. And I'm going to put it in meters. Some textbooks will put it in angstroms. I'm going to put it in meters. So let's do the HF first. This would be 9.2 times 10 to the minus 11 meters. That's how far apart the nuclei of the two atoms are in that particular molecule, in that particular bond. So the nucleus of hydrogen, the distance between that and the nucleus of fluorine is 9.2 times 10 to the minus 11 meters. HCl is a little bigger. I'm going to write it in the same exponent. It's 11.7. 11.27. Oops, I'm sorry. I'm getting the number wrong. It's 12.7. Times 10 to the minus 11 meters. It's just a little bit big, right? Well, that's a little bit bigger. It went from 9 to 12 or 9 to 13, so a little bit bigger. The HBr, the bond length there, is 14.1 times 10 to the minus 11 meters. And then finally for HI, it's 16.1 times 10 to the minus 11 meters. So those are the bond lengths. So notice what happens. The second element, fluorine, chlorine, bromine, iodine, those elements get bigger, right? As you go down the periodic table, the size of the atom gets larger. So the bond length actually increases as well. So HI is a bigger molecule than HF is. So that's the distance between the nuclei. That would be R. But next to that, I'm going to give you the dipole moment values. And I'm going to convert them to dBi, because those are more just more convenient units to use. Instead of having, 3.5 times 10 to the minus 31 coulometers. So the dBi, the dipole moments for HF is 1.82. For HCl, it's 1.08. For HBr, it's 0.82. And for HI, it's 0.44. So the point of that column is to suggest that what's happening is the amount of charge on each atom must be getting smaller, right? Because if you think about it, if the dipole moment is equal to the charge times the distance between the two particles, the distance between the two particles is increasing, right? It's getting bigger here. That's increasing. This is larger here. So if this is bigger, this should be bigger, right? But it's clearly not. This is the smallest value here. So that means the charge is getting smaller. Q must be getting smaller as you go down. Q is decreasing. Okay? Whereas up, so there you go. So why is it decreasing? The difference in electronegativities is what's happening. So if you look at HF, 2.1, 4.0, that's a difference of 1.9. But if you look at HCl, 2.1, 3.0, now the difference is only 0.9. And if you look at HBr, it's 2.1 and 2.8, the difference is only 0.7. So as the difference in electronegativity gets smaller and smaller, the charge on each atom gets smaller. And that's the key to understanding this, or it's an important point of understanding. As the difference in electronegativities gets closer between two atoms, the amount of charge on each atom gets smaller. And we can tabulate that through what we call the dipole moment. Okay? Now, one more thing to mention in this discussion. Okay, let me see if I can. There we go. I'm going to try to. Here's what we'll do. We'll come over here. Yep. Okay, I'll just have to come up here and erase some of it. There is a calculation we can do, which is called percent Ionic character. Okay? So it would be nice to have a nice little abbreviation. Your textbook doesn't really have one. So I'll create one here. I'll invent one. Percent Ionic character. And the percent Ionic character, let's put the formula down, is equal to the dipole moment that you measure or observed. Observed means you measure it. Divided by the dipole moment that's calculated assuming discrete charges. Okay, I'll have to talk about what I mean by that. Times 100%. Okay? Now, what is this percent Ionic character? The percent Ionic character essentially says, hey, if you have a purely ionic bond, for example, let's use cesium fluoride, CSF. Cesium has an electronegativity of 0.7. That's the lowest in the entire periodic table. Fluorine is 4.0. Your difference is 3.3. That's if you are going to have an ionic bond, CSF would definitely be it, right? That would be about as ionic as you could get, okay? So that we would expect to be 100% ionic, according to this formula, at least close to it, okay? Now, suppose we said we're going to have something that's purely covalent. Oops, sorry. If you have two atoms of the same element, they got to share electrons equally, so that's got to be purely covalent. You would expect 0%, right? 0% ionic character. It shouldn't be ionic at all. So what this formula does is it says, hey, someone's going to measure the dipole moment. So this is measured up here. Then you're going to calculate the dipole moment using the assumption that each atom has an entire charge, a discrete charge. So for example, if I did HCl, we would, because this one's more electronegative, we would say, hey, the charge on this one is +1, the charge on this one is -1, and so we're going to use that in calculating our dipole moment, okay, where we're going to use it like this. Dipole moment calculated equals Q, so now you just put in a charge of 1, plus or minus, doesn't really matter, times the distance. And the distance you would use is the bond length. Okay? So what happens is, if you start doing this calculation of percent ionic character for different substances, okay, you plot it. On the x-axis, I'm going to write electronegativity difference. And of course, the smallest difference we could have is 0, right? The largest difference we could have is a little bit over 3. But we could have somewhere around 1 or somewhere around 2. And then you calculate percent ionic character, okay? And that could go from 0 to 100%. And what you find is that if you take an element that's really highly electronegative, like fluorine, and combine it with something that's very low electronegativity, like potassium, the difference in electronegativity is above 3, and the percent ionic character is somewhere around 80%. Okay, so this is somewhere around 80%, and the difference in electronegativity is somewhere around 3.2 or 3.3. Okay, so it's not 100, even though we generally think of KF as being an ionic compound. According to this formula, according to this calculation, it's around 80% ionic, so that means there is some sharing going on. Now, take something that two atoms that have a very small difference in electronegativity, so I'm going to put that down here, and that's iodine bromide. Now, the difference in electronegativity between those two atoms is like 0.3, which is a very small difference. We would generally think of that as covalent. And so what you find is when you run it through this formula and calculate the percent ionic character, it's very small, meaning it is pretty covalent. It's primarily covalent. And if you look at the molecule HF, which has a difference in electronegativity of a little under 2, so here's HF, 2.1 and 4.0, that's a difference of 1.9. You end up with something that's not that far off. It's around 40%. 40% ionic and about 60% covalent. So in fact, even the substances we think of as being purely ionic are actually somewhat covalent, a little bit. And the ones that we think of as being covalent have a little bit of ionic character as well, and some are right smack dab in the middle. They're in between. So it's more complex than just something's ionic or covalent, ionic or molecular. It's actually a mix of all.